In this project, our goal was to build a machine learning classifier to predict whether a person has pre-diabetes or diabetes based on survey responses. We started by exploring the dataset, which contained approximately 110K survey entries. One of the first things we noticed was a significant amount of redundancy. We identified and removed around 7K duplicate rows to ensure our model won't be biased or repeated information. By visualizing and distribute the distribution of variables like BMI, age, and physical health, we confirmed that our target diabetes status was highly imbalanced, with far more non-diabetic cases than diabetic ones. This immediately told us that standard accuracy wouldn't be enough. We need to focus on F1's more. To better understand what drives diabetes risk, we generate a correlation matrix. This revealed that the general health, high blood pressure, BMI, and age was the strongest indicator of diabetic risk. For example, the, the health showed a correlation of zero point 0.3, and the blood pressure and age were 0.62 and 0.19. To improve performance, we focus on these health indicators and ensure that the model prioritizes features that capture the metabolic syndrome cluster. And after the cleaning, we compare three different models: Random Forest, CatBoost, and LabGBM. Random Forest provide a robust nonlinear baseline, and CatBoost was excellent at handling the categorical nature of survey questions without extensive preprocessing. LabGBM performed best overall in terms of training speed and handling the class imbalance. Because our data is imbalanced, we use internal weighting strategies like the is imbalance true in LabGBM and auto class weight equals balanced in CatBoost. These settings force the model to pay more attention to the minority diabetes class, which is crucial for public health screening. And in our GPM results, we achieved a final F1 square of 0.44 and a strong ROC and AOC of 0.81. Looking at the confusion matrix, our model correctly identified around 2K and 300 true positive cases. To maximize this performance, we did not rely on the default of zero point 0.5 probability cutoff. Instead, we shift our focus to recall, which reached like 0.78. In a medical context, false negative, meaning someone who actually has diabetes, is much more dangerous than a false positive, as it leaves a chronic condition untreated. By adjusting the decision's threshold, we balance this risk to ensure we capture as many risk individuals as possible. To access the fit of the classifier, we use a stratified train test split. This ensures that the proportion of diabetes cases remain consistent across our training and validation sets, preventing the model from getting a lucky or unlucky sample. We monitor the learning process to ensure we don't overfit. Since our training metrics and validation metrics follow similar trends, we are confident that model will generalize well to the new data. For future improvement, we would like to improve the model in two ways. One, external data, we could incorporate macroeconomic trends or regional data, such as access to healthy food, or local exercise facilities to see how environment impacts individual risk. Cross-validation, Instead of a single split, we would implement a stratified k-fold cross-validation to get more stable estimate performance. And production monitoring was deployed, we will monitor the data drift, checking if health profiles of population change over time to ensure the model remains accurate and useful for public health officials. That's all. Thank you.